All right, this is our second example and our final one as well. Then we'll be done with this episode. So I chose the apparent magnitude of a star because I'm biased and I like this stuff. But this is a really good example of a logarithm. So apparent magnitude, it's just a measure of the brightness of a star from Earth. And it can be modeled by this function where the apparent brightness, that should say apparent magnitude, but there's a difference. And so that's going to equal the absolute magnitude, which is considered the real brightness, if you don't consider distance or anything like that. And we add 5 times the log of the distance divided by 10. And that's a unit of parsecs, which is just kind of like light years, but not really. It's a little bit bigger than a light year. Okay, so if Alpha Centauri b, which is a star, has an apparent magnitude of 1.33 and an absolute magnitude of 5.71, we want to find its distance from Earth. So we are given little m, and we're given big M, and we want to find letter D. And the thing about that is because we have so much algebra going on, let's just solve for the variable D first, and then we can plug in what we have. So I'm going to start by subtracting big M on both sides. So we would get M minus big M equals 5 times the logarithm of D over 10. All right, then we're going to divide by 5 on both sides. So we'll get M minus big M over 5 equals logarithm of D over 10. So this is the point at which we have to get rid of the logarithm. And if we had been dealing with an exponential, then we would have taken the log of both sides. But now we're dealing with a log up front, and the way we want to deal with that is by raising both sides. I never know how to say this, like you make both sides into an exponent of a base 10. So you're raising both sides into exponents. And what's going to happen is 10 to the power of log base 10. I should say there is that understood base of 10 if they don't tell you. Just like if we had 5 to the power of log base 5, according to our composition rules, that's going to cancel, and that exponent is going to come down. So I will rewrite this over here. So we basically have 10 to the power of M minus big M divided by 5. That's all an exponent. And that's going to equal now D over 10. So pretty easy from here. We're just going to multiply by 10 on both sides. And that will isolate D. And then we can plug in what we have. So D equals 10 times 10. Little m is going to be 1.33. We'll do that in yellow. And then they told us big M is 5.71, absolute magnitude. And that is all divided by 5. All right, so we're going to plug everything in, and you get approximately 1.33 parsecs, which is just kind of a coincidence. Like, I saw that, I thought I did something wrong, but it's at the same distance as it is apparent magnitude for some reason. So yeah, that would be how you do that. Main takeaways is knowing how to get rid of that logarithm. That's important. All right, we have one more part to this question. Assuming that the star can change distances, we want to think about how the apparent magnitude relates to distance. Does the star get brighter or dimmer? I was very vague with this question with the intention that I would just show you. But if we're changing distances, that's going to be one of our variables. And we're comparing it with apparent magnitude. So really, we're just going to have apparent magnitude equaling. We're going to keep absolute magnitude as a constant. And the reason is because if we're changing the distance, that will definitely affect the apparent magnitude because it depends on that. But the thing with absolute magnitude is that it's at a fixed distance. So it's really just a constant for any object. So we'll just leave it as the 5.71. And then we're going to add, I'm forgetting things. Okay, 5 times the logarithm of d over 10. Okay, so again, we can kind of just like vaguely graph this on the side. Extend the page here. So if we had a graph over here, so we might want to think about, let's just ignore the 5.71 right now. We want to think about maybe what happens to that 1, 0 intercept, because that's kind of like our, the thing that we can compare different log functions with is that intercept. And we do know that if we plug in 10 for d, that's going to give us 1 in the argument itself, which must have, resulted in, which must have come from a 0 exponent. So 1, 0 is going to turn into 10, 0. So maybe that's like right there. But then we do add that 5.71, and so that's going to shift the whole graph up. So really, we're looking at 10, 5.71. You might be wondering about that 5 in front of the logarithm. We said that any number in front is just going to stretch or compress it, so that doesn't really change a whole lot. And then we just draw it through. It's really ugly, but it would look something like that, maybe a little smoother. And so, oh gosh, that is so bad. I'm going to redo it. But anyways, the question is asking how apparent magnitude relates to distance. And so we can see that we can use end behavior for this. As d is increasing as it's going to infinity, our apparent magnitude is also doing that. It's a positive correlation. So we know that apparent magnitude increases with distance, but then the question asks, is the star getting brighter or dimmer? And that's when we need to look at this chart right here with the yellow dots. So it turns out that the larger the magnitude value gets, the dimmer the star actually is. So really, the star is getting dimmer, even though the apparent magnitude is increasing. And I don't know, it was just some old man a long time ago who decided that would be the system, but yeah. Okay, and then one more part to this question. What is the concavity of the function? And what does it mean in context? So we already saw a problem like this, but we can see from the graph that it's concave down. And what we know about concave down is that the slopes are decreasing. So what do I mean by that? If we draw our tangent lines, you can see that it's super positive on the left, super positive, but then it just kind of flattens out as we move along the curve. So the slopes are decreasing. And what is our slope in this case? It's the rate of change. What is the change? That's going to be apparent magnitude. So This is kind of a lot to write. I'm actually going to type this, and that should be easier. So the rate at which apparent magnitude changes, let me move this down, is decreasing. So the rate of change is decreasing as distance increases. So that rate is changing, which basically means like the farther the star gets away, or moves away from us, I should say, it's not getting dimmer very fast anymore. It's just getting dimmer like more slowly and slowly as it moves away. And that's all you would really need to write for that question. Okay, that is it for logarithm applications. Thanks for watching.